I never made it, but I know what it takes. I'm motivated by a mix.
Hi, welcome to Basic Calculus. I'm Mamsh Helen, and our topic for today is on implicit differentiation. When we look at the definition of implicit, implicit means implied, not plainly expressed. Or in mathematics, it refers to a function which is not expressed directly in terms of independent variables. So we now use implicit differentiation when the function is not expressed in terms of y, in terms of one variable. So let's look at the table here. The examples on the left side are items which does not or which do not require implicit differentiation, whereas the examples on the right side are solved by implicit. I want you to observe them. What is the difference? Okay, so here on the left side, these are what we usually solved, right? We have y is equal to, or f of x is equal to, or g of x is equal to. These are explicit expressions, so because they are already equated to y or to f of x, whereas these are now implicit functions on the right side because your x or your y is mixed with the other variables. It's not directly expressed in terms of y. So if you observe this, this does not require you to use implicit because it's already equated to y. This requires you to use implicit because it's not yet equal to y. Same with these other examples. This do not require to use implicit. This requires you to use implicit. Okay, so that's an indication. So let's try this one. What if you have y is equal to x squared plus y squared plus 3x? Will this require you to use implicit differentiation? 5, 4, 3, 2, 1. Yes, this requires you to use implicit differentiation. Even if it's already equated to y, you would see that there is a y squared term here, which means that the whole expression is not yet expressed in terms of y and y alone. This is a term which is mixed with other variables, so therefore you have to use implicit. Okay, so let's have our first example. Oops. So, not yet. So, we'll use the notation. Okay, this notation, dy over dx, is a commonly used notation in differentiation, especially used in implicit differentiation, which was introduced to us by Gottfried Wilhelm Leibniz. So, this is read as the derivative of y with respect to x. But please take note that it's not always just y and x. Sometimes we also use different variables such as dv over dt, depending on whatever is given in our expressions. Okay, so in this case, for the sake of understanding the concept of implicit differentiation, we'll use dy over dx. And let's have our first example. Ito na, totoo na to. All right. For implicit differentiation, these are the steps that I personally like using. But if you find other references which tell you otherwise, but would still help you arrive at the same answer, then it's perfectly fine. Okay, but this is how I would do it. Step one is to indicate d over dx for all terms. For all terms. This means that we are getting the derivative of each term. Okay, so if this will now appear as d over dx times y, and then d over dx times x squared, and d over dx times negative 7. Next is to get the derivative of all of these terms. So we do that slowly, okay? Step 2 is to differentiate. Step 2 is to differentiate. Okay, let's begin with the first term. You are getting the derivative of y here. And imagine that you're just getting a simple derivative. Say I ask you to get the derivative of x. What will that be? You'll answer me with 1. Very good. Same concept with here. What will now be the derivative of y? Okay, it's going to be 1. There you go. Now, what will happen to the d over dx notation that we just placed? Here, we have to indicate the variable that we just took the derivative from. So, the derivative of y, we use the variable y. Therefore, your numerator now will indicate that you took the derivative of the variable y in terms of x. So, your numerator becomes dy, telling you that the variable you just solved is y. Look at it in comparison to the next term. What will be the derivative of x squared? All right, by power rule, you'll get 2x. And then, since your variable is x, the variable that you solved is x, then your numerator now would be dx over dx. dx ang numerator because you solved the variable x here. Now, how about this? This is a constant. What's the derivative of a constant? Okay, 0. Very good. Now, it's safe to say that we could use dx over dx here because technically, the expressions are usually terms and expressed in terms of x and y. So we choose to use dx over dx here because it's the main variable that we're using in the expression. Now, you could also say dy over dx, but yeah, let's just use dx over dx. And anyway, it will be multiplied to 0. So later, it will just be 0. Yeah, so we're getting the derivative in terms of x. Therefore, we choose a dx over dx. Let's simplify. dy over dx times 1 will just be dy over dx. By the way, that is for step 3. We simplify. And then we minus dx over dx. What will happen to dx over dx? Dx over dx will just be equal to 1. So 1 times 2x will just be simply 2x. And then dx over dx equals 0, times 0 will just be 0. And then we are getting dy over dx. This is what we're solving for, right? So for step 4, we now equate to dy over dx. All right. So if we have to equate in terms of dy over dx and I currently have negative 2x here, what should I do with it? Okay. Let's solve that again. Let me move this. Step 4, equate to dy over dx, or we have to look for the values in terms of dy over dx. And now we're given currently is dy over dx minus 2x equals 0. So we have a negative 2x that we have to remove. And how will we do that? Okay, we could transpose such that dy over dx na lang yung matitira. So you have dy over dx here, which is equal to positive 2x. And ladies and gentlemen, that's the final answer. Yep, we're done. That's it. So hindi po siya mahirap, matrabaho lang siya, right? So that's it. See you on the next video for another example.